Hello everyone. Today I will present our work titled Effective Code Membership Inference for Code Communication Models via Adversarial Promotes. This is joint work from Harbin Institute of Technology and Singapore Management University. I will explain the suite we study, our ADV promote MI method, the contributions and features we use, and the key experimental findings. Membership inference attack's goal is to decide whether a given code snippet was part of the target model's training dataset. The general process, including querying code X from the target model and labeling the output and X to make decisions. It matters in many situations, like assessing and mitigating the leakage of sensitive code. In code communication settings, we will observe that models often produce more stable outputs for members. Here is a motivation example to intuitively describe this phenomenon. Here are contributions. First, we propose ADV Promote MIA, a novel MIA framework. Second, we design 5 practical contribution strategies. Third, we conduct many experiments on multiply code LLMs and 2 widely used benchmarks. In our method, at first, we query the victim models with the original prefix and record the original output and the ground truth. Next, we design 5 code contributions that preserve functional behavior but alter service form. Then, we generate 11 semantic preserving variants prefix and query the model for each to obtain the perturbed output. After this, we embed ground truth, the original output, and each perturbed output with gold part. Finally, we compute cosine similarity and normalized perplexity for the outputs and aggregate them into a 27-dimensional future vector and feed it to a 3-layer MLP classifier to predict membership. We simulate a partial knowledge adversary that knows 20% of the victim's training samples. After this, we fine-tune models on the chosen training space to create victim models for evolution. These are our research questions. For RQ1 on human evil, our method achieves an AUC of 0.97, while baselines have AUCs in 0.48 to 0.58. On APPS, our method gets AUC 0.95, again substantially better than baselines. For RQ2, we omit future dimensions and contributions. Remove any single feature, reduce AUC. On human evil, the drop ranges roughly 2.1% to 10.3%, and on APPS about 1.1% to 4.2%. The single most important feature is the set-around deviations of similarity scores. This aligns with our core intuitions that variability under contributions is a key discriminator. We remove contribution types one at a time. Performance also fails. Removing IDLs causes the largest drop, up to about 16.5% AUC loss on human evil, indicating these contributions are particularly effective at explosion generation difference. This ablation shows that both contribution diversity and the choosing feature aggregation matter. On RQ3, we test our method on other code LLMs. Across these models, the method consistently achieves strong AUCs. On human evil, AUCs are above 0.91, and on APPS, AUCs remain high. This supports that contributions response single is shared across diverse code LLMs. On RQ4, we train the MIA classifier on one open source model and directly apply it to a different target model without retraining. Transfer AUCs remains high. The best case achieves 0.97. This indicates the perturbation-induced feature is largely transferable. On RQ5, we vary the attacker's null fraction of training examples from 5% to 25%. AUCs improve roughly 0.05 for each 5%, increasing up to about 20%, and the performance stabilizes thereafter. We also conduct cross-dataset tests. Our method still yields strong AUCs. To summarize, our methods leverage semantic preserving adversarial promos to reveal memorization in code LLMs. By combining perturbations with aggregation of similarity and perplexity, we obtain a future vector that yields high accuracy for membership inference. The method outputs prior baselines, generalizes cross models and datasets, and transfer well between models. Thank you for your attention.